Okay, so now we're ready to start dissecting the binary search algorithm within the context of Big O. But before we look at that, I just want to drive something home from the last couple of videos. In the last two videos, we noticed the algorithms had quadratic time, or they were in Big O of n squared. And that's because we're talking about the bubble sort and the selection sort. These are nested loop algorithms. And so that nested looping results in that n times n iterations, give or take, because as we've said before, we don't really care about total precision with Big O. So those were, again, nested looping algorithms that resulted in quadratic time. And now finally, with the binary sort, we're going to see a different type of algorithm that has a different type of Big O classification. So before we look at the code for binary search, I just want to recap, the whole notion of the binary search is that you keep cutting the area of interest in half. The area of interest meaning the portion of the array that you're searching. And, let's just, for fun, consider this donut. And if I keep cutting it in half, obviously it's getting smaller and smaller. And there's going to be a point eventually where there's nothing left, where I've cut it so small, infinitesimally smaller, that what I'm left with is, the barest minimum of a particle that can exist, like some kind of quantum particle. So the binary search is kind of the same way. So consider this array. We have 10 gelato flavors, and let's say I'm looking for chocolate. The algorithm is going to start at the midpoint. There is no true midpoint here because it's an even number, so it'll start right here on the hazelnut, and it's going to say, is chocolate what we're looking for less than or greater than hazelnut? If it's less than, great. We have eliminated this entire bottom portion, and now we can focus on this portion. Okay, so we've cut the array or the area of interest in half. And so the new midpoint becomes the midpoint of that new half. And, okay, so is chocolate less than or greater than coffee? And again, it's less than, so all right, great. I have narrowed it down to this half, okay? And so there's no midpoint here, but it'll probably land on the brownie chunk. That becomes the new midpoint, so to speak. And is it here, yes or no? I haven't found chocolate yet. So I'm up to 3 iterations through this algorithm. I still have not found the chocolate, but I know it's not here. And at this point, it's the moment of truth. It's going to look in this location, and it's either going to find the chocolate, which it will in this case, or if the chocolate were not in there, then we can conclude that it's just not in the array, period. So that was 4 iterations to find that chocolate for sure. Okay, so let's keep that in mind. Here's the code. I'm not going to dwell on it, but, basically, I talked about in the beginning of this video, those other 2 algorithms that we looked at for the bubble sort and the selection sort were nested loop algorithms. This is not that type of algorithm. Now, I should underscore here that we are talking about a search algorithm as opposed to the sorting algorithms in the previous 2 videos. So we're really kind of comparing apples and oranges here. They don't accomplish the same thing. But just to look at the overall style here, this is not a nested loop. And so we're not going to see that n squared that we saw in the other 2 algorithms. So this is just a simple loop. And we're landing on the midpoint. We're going to compare what we're looking for to what's in that midpoint. If we landed on it right off the bat, great. We're going to isolate that index where we found it, or else we're going to shift the midpoint, the new midpoint, either to the upper half or the lower half of the array. Okay, and that just keeps iterating over and over again until we either finally land on what we're looking for, or we can conclude that it's not in the actual array. Okay, so thinking in terms of mathematical expression of the binary search, the binary search is a logarithmic function of n with a base of 2. Base of 2 because we're always cutting it in half and cutting it in half and cutting it in half. And n, of course, is the size of the array in this case, all right? So we can also express that as this. It's the log of n with a base of 2. So that's like the, obviously the mathematical way of expressing that. So let's just do a very quick, let's put computer science for the most part out of our mind for a moment and just review what we mean by a log. A log is the power to which a base is raised to achieve some result n, okay? So, for example, we would say log of 8 with a base of 2 is 3. Because I have to raise 2 to the third power to get 8. Okay, so there you have it. 2 times 2 times 2 is 8. The log of 64 with a base of 2 is 6, because I would have to raise that 2 to the 6th power in order to get that 64. And then we have the 6 2's multiplied together to get the 64. So again, the log is the exponent that you're looking for to achieve some kind of final result on a base. Okay, so another thing I want to mention, thinking ahead to big O and algorithm performance, that a logarithm is the inverse of exponentiation. Okay, and so, this you've probably seen a chart like this in a math class recently, or maybe in high school even, certainly college algebra, and looking at, this is the exponentiation, and you see the growth is exponential. If this looks familiar, it's because we've been looking at a chart kind of like this when we're talking about big O and performance time of algorithms. So with the exponentiation, we go up into the stratosphere, right? With logarithmic growth, it really levels out over time. So they're inverses of one another. The logarithm takes a sharp turn to the right and flattens out. So kind of file that away in the back of your mind. We're going to come back to that when I sum this up at the end of the video. Okay, so we already said that the binary search can be expressed like this. It's a log of n with a base of 2, where n is the size of the array. In this case, n is 10 because I've got 10 elements in the array. And, when I ran through this, when I was finding the chocolate and earlier in the video, it took me four iterations to find that chocolate, and that was the worst case scenario. And so, if the log of 10, the log of 10 with a base of 2 is actually 3.32 something. Let me see here. I just pulled this up online. So the log of base 2, okay, the common base is there, and looking for a result of 10. There we have it, 3.32, give or take. Okay, so getting back to this, hang on here, sorry. Okay, so log of 10 with a base of 2 is 3.32, and we would round up to 4 to get the worst case scenario for binary search. And you saw when I was looking for the chocolate, it took me 4 reps, 4 iterations of that algorithm. Another way to think about this is, these are kind of well-known logs because you have a nice clean result. Log of 8 to the base 2 is 3, we've already mentioned earlier, and then log of 16 with a base of 2 is 4. My array size, 10 items, n equals 10, lies between these two numbers, okay? So it's like somewhere in the 3 to 4 iterations is what you're going to end up with. And, to get the absolute worst case scenario, you would have to round up and go with the 4, go with the higher number in that case. Okay, so expressed as big O, we would say the binary search algorithm is in O, or is in big O of the log of n with a base of 2. Okay, where n is the size of the input, or the input in this case being the array that we're searching, the binary search. And, by now, how imprecise big O is. It's almost like we don't even have to care about the base of 2. I can even lose that and strip that down and say it like this, in the big O of log of n, okay, and not even care about the 2. So in any case, we would say the binary search runs in logarithmic time. Okay, and getting back to this chart that we've seen before, we saw the n squared twice already with the bubble sort and the selection sort, and we saw the exponential growth, and the growth meaning the execution time. Okay, so exponential growth is bad when it comes to algorithms. Now, here we have logarithmic time as the blue line, which levels out. As the input gets much larger, the growth is much slower and it starts leveling out. So that's a slow growth algorithm in comparison to the n squared for sure, and that's a good thing. So and again, this is a search algorithm. The other two were sorting algorithms. We're comparing two different things, but just to give you an idea of some of the big O classifications and what's good and what's bad, this was an example of something that's not so great. Not great at all. And then this is something that is much closer to what you would aim for if performance in a program is critical. Okay, so I should be able to tie everything up in one more video. I have two quick algorithms to talk about, and then we'll sum everything up at the end.